All right, welcome. Today, we're going to dig into something really interesting, a fundamental rule of circuit analysis. One of those rules they teach you in your first engineering class. But what if? What if that rule is actually a myth? Let's dive in and find out. I want you to think back to your engineering classes, specifically about the principle of superposition. It's this super powerful tool, right? It lets you take a complex circuit, solve for each power source one at a time, and then just add up the results. Simple. But you're also told there are these sacred, unbreakable rules. Well, guess what? Today, we're going to break one.
Okay, so first things first, let's lay out the established rule, the dogma, really. For decades, pretty much every textbook and every professor has drilled the exact same thing into students' heads when it comes to one particular component, the dependent source.
So just a quick refresher, circuits have two main kinds of sources. You've got your independent sources, like a battery. It just has a fixed value, that's it. But then you have these other things, dependent sources, which you can see over on the left. They're different. Their value isn't fixed, it's controlled by some other voltage or current somewhere else in the circuit. Think of them as being puppeteered by another part of the circuit. They're super important for modeling stuff like transistors.
And here it is, the rule itself, laid out in no uncertain terms by the classic textbook from Centuria and Wedlock. It says, and I'm paraphrasing here, the answer is very simple. Never, ever suppress a dependent source. You apply superposition to the independent sources, sure, but the dependent ones, you leave them alone. It's not a suggestion, it's presented as an absolute ironclad law.
So, you might be asking, why is this rule so strict? Well, there's a classic go-to example that seems to prove it beyond a shadow of a doubt. Let's just walk through it real quick, because seeing what happens when you break the rule, it really makes it seem like a solid law. Okay, check out this simple circuit. We've got one independent voltage source, Vs, and one dependent voltage source. Its value is just A times Vs. Now, if you do a quick analysis, it's pretty obvious the output voltage, VO, is just going to be A times Vs. Simple enough, right? That's our correct answer. Let's lock that in our memory.
All right, now let's try to use superposition, but we're going to do it the wrong way, the way the rule says not to. First step, let's find the output caused by the dependent source alone. To do that, we have to suppress the independent source, Vs, which means we short it to ground. Well, if Vs is 0, then the value of our dependent source, which is A times Vs, also has to be 0. So the first piece of our output, let's call it VO1, is just 0. Easy enough.
Okay, now for part 2 of our illegal calculation. We bring back the independent source, and now we suppress the dependent one. Remember, suppressing a voltage source means you just replace it with a plain old wire. But look what that does. It shorts the output terminal directly to ground. So our second piece of the output, VO2, is, you guessed it, also 0. So here's the big finale. We add our two results together. V1 plus V2 equals 0 plus 0, which is 0. But wait a second. We already know the correct answer is A times Vs. So this is just flat out wrong. Totally wrong. See? This is why the rule exists. Case closed, right? Never, ever suppress a dependent source. Seems pretty convincing. But what if it's not quite that simple? What if that whole demonstration was flawed? Enter a mysterious, unpublished paper from 1994 by a guy named W. Marshall Leach, and he called this entire long-standing rule a misconception. I mean, this paper was basically academic heresy. Leach sent it off to all the big journals, and you know what? They all rejected it. But he stood by his claim. He argued that decades of textbooks had it all wrong. He said you absolutely can suppress dependent sources. You just have to do it the right way.
So how on earth did he do it? How do you break an unbreakable rule and still get the right answer? Well, let's take a look at his controversial method.
Okay, here's the absolute key to understanding this. Leach's big insight was this: you can suppress a dependent source, but with one massive caveat. When you're calculating its contribution, you do not let its controlling variable go to 0. Instead, you freeze it. You treat the dependent source like it's an independent source, with its value locked in. And what's that value? It's the value that the controlling variable had in the full original circuit before you started messing with anything. Let me say that again, because it's the whole shebang. You use the value from the original complete circuit.
All right, to really see this in action, let's use a different, better circuit. Now, if you just go ahead and solve this thing using any standard method, say nodal analysis, you'll find that the current I is exactly 1 amp. and the voltage Vx is 5 volts. So let's keep that in mind. The correct answer for Vx is 5 volts.
Okay, now let's apply Leach's method step by step. First, we'll figure out the contribution from the 5 amp independent source, which means we suppress the dependent source for now. Then we do the opposite. We look at the contribution from the 4I dependent source, so we suppress the 5 amp independent one. But here's the crucial third step, the magic trick. We don't let I go to 0. Remember, from our original analysis, we know that I is 1 amp. So we're going to treat that dependent source as if it were a totally independent 4 amp source. And then finally, we just add the two results.
And when you actually run the numbers, the result is pretty amazing. The part of Vx coming from the 5 amp source works out to be 3.261 volts, and the part from our dependent source, the one we treated like an independent 4 amp source, is 1.739 volts. You add those two together, and what do you get? Exactly 5 volts, the correct answer. It works. It actually works. The unbreakable rule just got broken.
I mean, that is a pretty shocking result, right? It goes against everything we're taught, so you have to wonder, did anyone else look into this? Did this just disappear into obscurity? Nope. Another academic, a guy named Robert Damper, decided to take on the task of analyzing this heretical idea.
And what did he find? Well, Damper confirmed that Leach's method was in fact absolutely correct. He did find one tiny subtle flaw in Leach's original mathematical proof, but he was able to correct it. And by doing so, he put the entire method on rock-solid theoretical ground. So now we have a fully proven mathematically valid method that just flies in the face of the textbooks. And this actually brings up a really brilliant, deeper point that Damper made. He said, look, we have to remember what circuit theory really is. We're not playing with actual physical wires and resistors on a breadboard. We are making mathematical manipulations on an abstract model of a circuit. And in that abstract world of math, Leach's method of freezing the dependent source's value, well, it's a perfectly valid mathematical operation. It's no different than, say, inverting a matrix.
Okay, so where does that leave us? We've got two methods that seem to completely contradict each other, but they both seem to work. How is that even possible?
Well, it comes down to how you look at it. The standard method, the textbook way, it works because it's a perfectly valid mathematical shortcut. It basically treats the dependent sources as just part of the circuit's fabric, lumping them in with all the resistors and other passive components. Leach's method, though, you could argue it's a purer form of superposition because it treats every single source, whether it's independent or dependent, individually, one by one.
Ah, but hold on, there is a catch. There's one really important place where the old rule never suppress a dependent source is still absolutely critical, and that's when you're finding Thevenin or Norton equivalents. Now, why is that? The reason is pretty subtle but super important. See, superposition, the way we've been using it, solves a fixed circuit. It's static. But Thevenin's theorem is all about characterizing how a circuit behaves as the load changes. And as that load varies, guess what else varies? The controlling variables for those dependent sources. They're not constant anymore. So you can't just use Leach's trick of freezing their value because their value is no longer frozen in the real application. So after all that, what's the big takeaway? Is this just some neat academic party trick? I don't think so. I think it's something much bigger. It's really a lesson about the nature of rules themselves.
This whole story really shows that sometimes the unbreakable laws we learn in science and engineering are actually just very useful models or really clever shortcuts that only apply in specific contexts. The rule against suppressing dependent sources isn't necessarily wrong. It's just a tool for a specific job. And once you understand why a rule exists, that's when you earn the right to know